Hello everyone, my name is Benjamin Sliwa. I'm a PhD student at the Communication Networks Institute of the TU Dortmund University. My talk is about the LIMoSim framework, which brings together mobility simulation features for aerial and ground-based vehicular systems. The talk is structured as follows. At first, I'm going to motivate the integration of UAVs into the next generation of intelligent transportation systems. Then I'm going to show a proposal, LIMoSim, for joint simulation of aerial and ground-based vehicles, give an overview about different features of the proposed framework. Then we are going to discuss a case study which focuses on UAVs as aerial sensors, and finally the talk is concluded. Hybrid intelligent transportation systems aim to overcome the limitations of purely ground-based systems through integration of aerial vehicles. This then catalyzes the development of novel applications and services such as aerial network provisioning, where we have multiple UAVs which are connected to the cellular network, and they hover dynamically the centroids of clusters of ground-based vehicles in order to provide network coverage. There's also aerial sensing. So here we have an UAV which observes an accident, then warns nearby vehicles and also reports its measurement data. Another application is UAV enhanced near field delivery. So here we have a moving truck and different UAVs which collect packets, deliver those packages, and then they meet the truck again at the rendezvous point and pick up more packages. However, for developing these novel applications and services, we are confronted with different research challenges. The first one is the interdependency between the mobility and the communication technology. So this then refers to optimizing the radio channel robustness between the different mobile entities. We also need to pay attention to the interactions between the mobile agents and their environments. This means, for example, that UAVs need to detect buildings as obstacles in order to allow collision-free path planning and also in order to allow to improve the radio network quality. One enabler for this is the anticipatory mobile networking paradigm. So here you see an example where we jointly use mobility prediction together with radio environmental maps in order to get estimates for the signal strength at the future location. With LIMoSim, we aim to provide a joint framework which provides the simulation of ground vehicle mobility, mobility of aerial vehicles, and also the communication systems based on ns-3. The main component of LIMoSim is its mobility simulation core, which is embedded into the ns-3 setup using a shared codebase approach. This means that the different entities of the different simulation domains can interact on a C++ pointer level, and there is no inter-process communication also involved in order to connect the frameworks. We also have an optional 3D visualization, which is based on OpenGL. Within LIMoSim, all vehicle instances are created using the Vehicle Manager class, which then connects to an interface in ns-3, and this is then linked to a mobility model of the ns-3 core. We have native support for OSM map data, which is used to create a virtual world, which consists of road network topology and also has buildings. Those buildings are used as obstacles for the mobility, especially for the UAV agents, and also as attenuators of the radio channel. So we have an attenuation model here, and this is then linked to an abstract channel model for LIMoSim in ns-3, and then finally linked to a real channel model of ns-3. In order to interconnect the simulation control, we also have some links on this level then, which connects the schedulers of ns-3 and LIMoSim. Within LIMoSim, all vehicles are derived from an abstract base class, the LIMoSim vehicle. Then we have the LIMoSim car and the LIMoSim UAV, and both of them make use of an hierarchical mobility model. For the car, we have the strategic model, which is responsible for the high-level mobility, such as target definition, path planning, and routing. On the lower end, we have the follower model, which is responsible for adaptive cruise control, the safety distance keeping between different cars, and also for the intersection approaching. For the UAV, we use the action selection to define the general behavior, such as the task of an agent, and this can also be used to define different roles of agents. Here's an example shown where we have a mobile delivery scenario, and on this level of mobility, the task would only say deliver the packet to the destination. Then we have the steering level, and here we have specialized routines, and they're responsible for collision avoidance, for task fulfillment, swarm coherence. And if we now consider this example here, then our UAV would recognize the other UAV and perform a collision avoidance maneuver. It would also plan the path, and this corresponds to the desired movement. Finally, we have the lower level mobility, which is the locomotion. And here we have the physical platform capabilities. We have 3D acceleration and also the power consumption. So here in the example, it would show the actual movement of the next time step. And this is then this component here. Each vehicle also has an awareness module, and this is meant as an enabler for anticipatory communications. So here we have mobility prediction, we have some knowledge about the mobility behavior of the other vehicles, and also are aware of our network quality. In the following, we will show a short video sequence about a UAV-enabled pickup and delivery scenario. So hereby we have two UAVs, and they pick up packets from a moving truck. They deliver the packages, and the process for delivering is modeled as a traveling salesman problem. And those vehicles coordinate themselves via LTE. Use the following color coding for the buildings. So orange ones are the current active delivery targets, the green ones are the successful deliveries, and the red ones are the future deliveries. So at the beginning, all UAVs follow the truck quite closely, and then one of the UAVs delivers one packet to its current delivery target, which is then marked as a successful delivery, and then it tries to reapproach the car in order to pick up another packet and deliver it. Here you can see an overview about the simulation scenario and the simulation parameters. So the map shows the campus area of the TU Dortmund University and the surroundings. We position the node Bs according to their real-world locations. We use the setup to implement a case study focusing on aerial sensing, where we have multiple pairs of UAVs and cars, and each UAV aims to stay close to its corresponding car, but keeps a fixed altitude offset. Each 100 milliseconds, the UAVs transmit cam messages to their corresponding cars in order to keep their situation awareness up to date. Then we compare the end-to-end performance of different communication approaches. We have a centralized approach, which is modeled as an LTE setup using the LENA framework, and also have a decentralized approach where we use 11P based on WAVE and also Cellular V2X. And here you see the results for the packet delivery ratio and for the end-to-end delay. It can be seen that the centralized approach shows a lower PDR than the decentralized approach, which is due to the involvement of the node B, which results in a higher probability for non-line of sight situations. If we consider the link between car and node B, we can see that the angle between those two is quite flat. If we have a building in between, then we are likely facing a shadowing situation. However, for the decentralized approach, we have a single hop direct communication link with a very, very steep angle, which minimizes the probability for non-line of sight situations. If we now consider the 3GPP robustness requirements, then we still see that our communication technologies are able to fulfill them quite well. For the delay, we can see the difference between coordinated medium access and direct medium access. So the coordinated medium access implemented by LTE results in a higher delay, and the direct medium access obviously results in a low delay, whereas the cellular V2X applies a semi-persistent scaling, which results in a slightly higher delay than for the 11P approach. Now we take a short look at the temporal behavior of different indicators. At first, we consider the multidimensional acceleration model. So here you see the acceleration in X, Y, and Z direction. And for the Z direction, you see that it's constant because the mobile agent operates at a constant height. We use a low-level mobility model from literature here, and we wanted to make sure that the model is using a system-level consideration rather than highly complex modeling of individual rotors. Therefore, the complexity can be compared with the follower model complexity of the car agent. We also have a model for the propulsion-related power consumption, also from literature, and this is a function of the acceleration here. And there's a related research field, which is the joint optimization of the trajectory design and the power consumption of the mobile vehicle. Finally, here's a plot for the RSRP, so the signal strength which is received by the different vehicles. So at first for the E0B UAV link, you can see here that it's more or less constant. There's a non-abstracted line of sight. And for the car E0B link, we see that this link is more impacted by the buildings in the scenario, and there are also situations where the car experiences sporadic link loss. Now I'm going to conclude. We proposed the lightweight ICT-centric mobility simulation framework, in short LIMoSim, for the joint simulation of aerial and ground-based vehicles, which provides seamless integration into ns-3 via shared codebase coupling. In future work, we are working on support for more complex road network topologies. We are also working on a UI-based scenario editor, and we consider different machine learning methods for mobility control, especially reinforcement learning. Thank you very much for your attention.